Hi everybody! Do you remember the tilted square grid shader we created here some time ago? If you liked it and would like to try something similar but more irregular, you might be interested in this tutorial where we'll create an effect similar to a stone mosaic, which can be a very interesting feature in many games. So let's get started. I think it was over a year ago when I created a shader here that displayed a moving Voronoi diagram. Back then, it was just a tutorial without any particularly interesting use case, but this time, the principle of such a diagram will come in very handy. We're going to create our mosaic using this Voronoi algorithm, but with a much higher cell density, and we'll add sharp edges between them to better separate the individual pieces. So I'll create a new 2D scene and insert a typical screenshot from our game, to which we'll then assign a new shader. Right-click, create new scene, and let's call it mosaic. Very well, 2D scene. Okay, and now I will find our texture here. It's the fountain JPEG, and the Sprite 2D node was automatically created. Let's go to the inspector and cancel the offset, the centered, and in transform position, let's reset to 0, 0. Very well. Let's scroll down to the material section, open material, and create new shader material. Click, create a new shader, mosaic GD shader, canvas item type, and let's put it to the shaders folder. Create, and click again to open it in the shader editor. Okay, and we'll go through the usual setup, which involves deleting the unnecessary code so that we are left with just a fragment function. So I'll delete the vertex function and I'll delete the commented out light function. Okay, so the shader will have several uniform parameters and that we can configure it as needed. We'll want to define the number of tiles, the contrast to better highlight the colors, the thickness of the lines between them, and as a bonus, a value for gamma correction of the final image, like this. Uniform float tiles with a hint range, and the initial value would be, for example, 80. And let's put the range, let's set the range as from 4 to, for instance, 256. Okay, now the second one, uniform float contrast with another hint range, and the initial value I'll put to 2, and the range would be from 1 to, let's say, 10 with the step point 0.1. The third one is, as I said, the thickness, uniform float thickness, a hint range, and it starts at 0.5, and the range would be from 0 to 4, again with the step point 0.1, and finally the gamma correction, uniform float gamma, hint range, and the optimal value is 2.2. As you may remember from the tutorial about the ray marching technology from 1 to 4 and the step point 0.1. Alright, by the way, the value of the tiles parameter isn't actually the total number of tiles, but rather the number along the shorter side, that is the y-axis. Still, I didn't feel like using a longer name. Very well, so to save ourselves some work, we'll reuse as much code as possible from the original Voronoi shader I showed a moment ago. First, I'll copy the function for generating a pseudo-random vector, which will be necessary for the mosaic-like shape of the final effect. Without it, we'd we just end up with a square grid. All right, but I have to find it first. It should be here in the shaders folder, and let's scroll down to find something like v.gd shader. Where is it? Here. Yeah, this is it. So as I said, the function, it's called n22 here, but I think our usual name is hash22 now. So let's just rename it. Very well. The algorithm for calculating the Voronoi diagram will be a bit longer this time and include some small differences, so it makes sense to separate it into its own function. We'll write the skeleton of that function just before the fragment function. So right here, vec3 Voronoi with the parameter vec2 p for the current point, and let's for the time being return just the zero vector, vec3 0. Okay, you might find it strange that this function returns a vector 3, even though we are still working in 2 dimensions. That's because this time it's not enough to just know the minimum distance to the nearest cell. To properly set the pixel color, we also need the coordinates of the cell, which would be a vector 2, and the distance to the nearest edge, which is supposed to be a float. From those, we'll construct a vector 3. Before we dive into implementing the Voronoi function, let's also write the basic structure of the fragment function, which we'll call it. We'll start with the usual aspect ratio adjustment based on the dimensions of our image to prevent the resulting grid from being distorted horizontally. And we'll shift the coordinate origin to the center, giving us a pivot point for smooth zooming in and out. So let's delete this comment and write the code I just mentioned. Resolution is 1 divided by texture pixel size. This is what we know very well from previous tutorials. And now vec2 UV is, as I said, UV minus 0.5, moving the origin of coordinates to the center of the image, and finally the aspect ratio recalculation. UVX is multiplied by resolution X divided by resolution Y. Great. Next comes the call to the Voronoi function. As a parameter, we'll use the UV vector, to which we apply the zoom factor. In other words, the tile grid density, by multiplying it with the tiles parameter. And to normalize the result back to UV coordinates, we then need to divide it, the result by the same parameter. So it would be like this. Vec3 V for Voronoi is Voronoi of the parameters, as I said, UV times tiles, the zoom factor, and the result we want to divide by tiles. Okay, so what's next? We have a vector 3 that we need to process into the final pixel color. We know that the first 2 components contain coordinates, so we'll assign them to a new variable. Let's call it vec2 vuv, like Voronoi UV coordinates, and as I said, v.xy, the first 2 components. If we were to use the vector vuv, now, to sample a pixel from our image, we would end up with a square image shifted to the bottom right corner. That's because we applied a coordinate origin shift here and an aspect ratio adjustment, which were necessary for calculating the Voronoi diagram. But to display the image properly, we need to reverse those operations. So first, I'll recalculate the VUV vector back to the original image dimensions and then move the origin back to the top left corner. So the inverse operations are like this. vuv.x is multiplied by this time resolution y dot y divided by resolution x. So it's the reverse order of these operands. And finally, vector 3 color is, we are reading from our texture and the texture variable, but the coordinates are VUV plus 0.5. So now we reverse both operations. RGB, because texture function, as we know, returns vector 4, so we need only the RGB components to form the vector 3. Okay, so we have the pixel color, which will now finally display. Color is vector 4, that is composed of vector 3 color and 1 for the alpha value. So, as we can see, an orange color is being displayed, which is probably a pixel near the center of the image. This is because the Voronoi function currently returns a 0 vector, so to which we add 0.5, which is why we take the color of the pixel in the center of the image. So it's time to improve this algorithm. We'll go back to the Voronoi function and write the first part of the calculation, the diagram itself. The code will closely resemble what I wrote a year ago for the original Voronoi shader. Basically, we are dividing the image into a square grid where we apply certain deformations to each cell. And as we know from previous tutorials, the best functions for calculations of such a grid are floor and fract. The former gives us the ID of a specific cell, while the latter gives us the local coordinates of pixels vector that cell. So let's do it here. Vec2 grid UV is fract P. Okay, I think I should start with the floor, so let's put it here. Vec2 grid chords is floor P. This is exactly the code from the original Voronoi shader. Next, we'll prepare variables to store intermediate results, which will eventually give us the values that the function returns. For the minimum distance, we'll start with a large number to ensure that in the upcoming comparisons, we will definitely get to smaller ones. Okay, so let's prepare them. Vec2 min offset and vec2 min vector. And as I said, let's start with some high min distance. Min dist is 100. Very well. And now comes the calculation, which will run in a double loop, because for the given coordinates, we want to find the nearest cell in the entire grid. It's important to note that here that we won't be searching the entire grid, as such a computation would become too slow with a higher number of cells, which in the case of a very dense mosaic could be more than 10,000. That's why we only compare with the nearest neighbors, which means the cells in a 3x3 grid, like this. For float y starts at -1, y is less or equal to 1, and y++, this is the first cycle, and the second one for float x from -1, of course, and the same conditions, 1x++. All right, so let's continue. For each of these cells, we determine its offset, then a random displacement using our pseudo-random function, and finally a vector whose length tells us whether we found the cell closest to the given pixel. And if we have, we store all the values we've obtained. By the way, the more detailed description of this Voronoi algorithm is included in the original video of the former shader. So if you're interested in the details, please check it out as well. All right, so the offset. Vec2 offset is simply a vec2 of these two shifted values, x and y. And now vec2, let's call it shift, and it's the result of the hash22 function applied on grid chords increased by the offset. So for each cell, we'll just define a pseudo-random shift. Now the vector to the nearest cell is offset plus the shift value minus grid UV. This one. All right, now we need to check the distance, but we know that the function dot product is basically a squared distance, so we can use that and it should be computationally faster. Float squared dist is a dot product of vector. Okay, and it's time to compare it with the current minimum distance. If squared dist is less than min dist, then let's set the new values for all our variables. Min dist is square dist. Min vector is the current vector. And min offset is the current offset. Okay, and now we can return the result of the calculation to the fragment function. We need the local coordinates of the pixel offset by the minimum offset. And also the minimum distance. That distance isn't in its final form yet, but we need to put something into the vec3 so the shader can compile. It would look like this. So as I said, grid coordinates plus minimum offset and minimum distance for the edges. And of course, I made a typo when I wrote the code right here where the first cycle starts. It's supposed to be, of course, -1, not +1. And now the diagram should be correct. And we have our first result. If we take a closer look at the image, we can see that it truly is a Voronoi diagram, and the colors match the pixels that are located in those areas of the original image. We can try changing the tiles parameter to confirm that we really do have a pivot point in the center, which allows us to create fade-in and fade-out effects like this. Let's find it in the shader parameters, and I will decrease the tiles, or I will increase it. Looks pretty cool, doesn't it? Okay, let's get back to 80, the default value. However, to really make the result look like a stone mosaic, we still need to add the lines between the tiles. So let's go back to the Voronoi function and write the second part of the algorithm. I will expand the area a little bit, and here it is. This is the first part. And right here, we will write the second part. It will be very similar to the first one, only the distance calculation, this one, will differ. So we reset min dist to its original value of 100 and copy the whole double loop, like this. Min dist is, again, 100, and I will copy and paste this whole section. This whole block. Copy and paste. Okay, let's just display all of that. Very well. So at this stage, we only want to modify the min dist. So let's get rid of these two lines. Only min dist is assigned a new squared dist value, and we need to change the distance calculation, which now should be the distance to the edge of the respective cell. So it would look like this, not dot vector vector, but dot min vector plus vector, and here we want to normalize the difference between the vectors, so the direction. Normalize, and it will be vector minus min vector. Okay, and yeah, that's it. That should complete the Voronoi function. And now we just need to display the edges we obtained. As we know from the other tutorials, a smooth line can be calculated using a smooth step function, where we use the obtained distance, the z component of the vector v, as the third argument. So I will add it right here after the color definition. Color is multiplied by smooth step, and now 0.001, 0.001 plus the thickness parameter, and it's too big, so let's divide it by 100, multiplying by 0.01, and finally v dot z and semicolon. Okay, nice. Let me just show all of that and zoom in a little bit, but the image might be a bit too contrasty. So let's try adjusting the contrast using the uniform parameter we introduced at the beginning, and it's called contrast. Okay, so right here, before we create the grid, color is the power function of color, and vector 3 contrast right there. All right, and it seems we forgot about the gamma correction. So one more line before the final assignment of the color right here. Let's add the usual line. Color is power of color to the power of 1 divided by vector 3 gamma. Okay, and we are done. We can now play around with the parameters. If, for instance, we lower the contrast to the minimum, like this, we get a mosaic that resembles something like sun-faded sandstone, which can be further enhanced by increasing the gamma correction, like this. Yeah, this is a pretty cool effect. So let's reset. Or if we reduce the thickness to the minimum, so the edges are barely visible, and increase the tiles to the maximum value of 255, we get a very fine mosaic. We can zoom in on the image to see that it's still formed by the Voronoi pattern, and it looks very good from this perspective. Okay, let's get back and reset again. Thank you very much for watching. This kind of effect will definitely find use in many projects, and I just thought about how I'll incorporate it into my 3D adventure game that I've been working on for some time now. Hopefully, I'll be able to showcase it here someday. As possible future improvements of this shader, we could consider changing the values in the pseudo-random function #22, which should give us slight variations in the final diagram, or adding a new uniform parameter to set the color of the lines between the tiles. Anyway, I hope you enjoyed today's tutorial. So take care, good luck with your projects, and I'll see you in the next video.